An old trick in lecturing that usually doesn't work is to say that if anybody spotted the deliberate mistake last time, then we'll offer some reward. I don't propose to do that. However, in not transcribing directly from my notes onto the blackboard last week, a couple of the lines where I was writing down stochastic order terms, I'd in fact got the stochastic order terms wrong. The end result is correct, and those are the lines involved in the derivation of the Akaike information criterion. The end result is correct, but if you look at two of the lines intermediate in the derivation, some of the order terms, instead of being of order t to the minus 3 upon 2, should in fact have been of order t to the minus a half. But the end result was correct. All the hypotheses that we've considered previously have been simple null hypotheses against simple alternative hypotheses. And in practice, most of the null hypotheses that we're interested in are in fact joint or composite hypotheses. And if we return to the usual example of the linear regression model, where we partitioned the regressors into x1 and x2 and consider the null hypothesis beta 2 equals 0, I ought at this stage to emphasize that beta 2 is in fact a vector of k2 coefficients, so that this hypothesis is a composite hypothesis in the sense that it embodies the hypotheses k1 plus 1 is 0, beta k1 plus 2 is 0, and so on down to beta k2 plus k1 is equal to 0. And there are situations when, if we test directly this composite hypothesis against the maintained and reject it, we want to gain more information from the data set than we've got as a result of that single test. In other words, if we perform the f-test of h0 and reject it, then it's possible that we could from the data find out which, if any, of these individual hypotheses which make up h0 was responsible for the rejection. And in situations like that, we have to take account of the fact that h0 is a composite hypothesis. However, before I go on to discuss methods by which we can find out which, if any, of these hypotheses was responsible for a rejection, I must emphasize that if all we're interested in is h0, then the most efficient and statistically powerful test of that is the f-test. We're only interested in these other procedures which consider the individual hypotheses which make up h0 if in fact we have an interest in these individual hypotheses. If our only interest is in fact in h0, then the f-test is the appropriate test. When we are interested in the individual hypotheses which make up a composite null h0, then the testing is in fact much more difficult. And a simple example illustrates the problems that arise. If now we consider a regression model in which there are only two regressors, x1 and x2, we assume that the errors ut are normally distributed with zero mean and constant serially independent, constant variance and are serially independent. And in addition, we assume that the x1 and x2 variables are orthogonal. so that in the matrix terms we're assuming that x prime x is some scalar transformation of the identity matrix, which simplifies the situation. And if we then specify our null hypothesis to be beta 1 is equal to beta 2, which is equal to 0, then immediately we know that the appropriate direct test of H naught, the F test, would be r squared upon 1 minus r squared t minus 3 upon 2 when all the variables y, x1 and x2 are in fact measured as deviations from the mean, so that implicit in the model there's a constant term as well. Hence 3 variables being estimated. And we would compare that statistic with f2 t minus 3. But that still has the problem that if we are in fact interested separately in the hypothesis h1 that beta 1 is 0, and also in h2 that beta 2 is 0, if when we test h naught using this f test we have a rejection, we haven't found out whether in fact both of these are rejected, and we might be interested in that. Well, if we look at the problem, we have a maintained hypothesis, which is this original linear regression model with all the variables in. We then have H1, which is a model which excludes the variable x1. Also we have H2, which is a model which excludes the variable x2. And then finally, we have H0, which excludes both x1 and x2. The f-test in this diagram can be represented by a direct test of h0 against hm, the maintained. There are, as we can see from this diagram, 2 other ways we could go about testing h0. We could, on the basis of a t-test on the estimated coefficient beta 1, test h1. And then, if we don't reject that hypothesis, we could go on to test h2. In other words, we can go down that leg, and we would, at this stage, have done a t-test on beta 1. If that doesn't result in a rejection of h1, we would then go on and do a t-test on beta 2. If that also doesn't result in a rejection of h2, we have at that point not rejected h0. However, if when we're on this first leg, we found a significant t-ratio and we were rejecting h1, then we could have the decision rule that because we've now rejected h1, h1 is a constituent part of h0, we now reject h0 at that point. So that gives us an alternative sequential method for testing h0. We test h1 first, and then if h1 isn't rejected, test h2. But given the lack of structure in this particular problem, we could also have a sequential procedure which tests h2 first via a t-test on beta 2, and then if we don't reject h2, go on to test h1 via a t-test on beta 1. And if we don't reject both h2 and h1 in that sequence, we wouldn't reject h0. And that gives us another sequential method of testing h0 against the maintained. And the question now arises, which of those procedures, the direct test or the 2 alternative sequential tests, is going to be more powerful? Or is there one of those which is the most powerful? testing procedure. If there is, then that would have some desirable statistical properties, and we might want to use that procedure in preference to the others. Unfortunately, as is well known for composite hypotheses, it's quite possible that a uniformly most powerful testing procedure or test statistic needn't exist for composite hypotheses. And we can see that a uniformly most powerful testing procedure in this case doesn't exist by a diagram that we're now considering the space in beta 1 and beta 2, and the origin here would be the hypothesized values for beta 1 and beta 2. So in this example, the origin here is in fact 0. And what we have in this square is in fact if we're now testing when we do the t-tests at, say, the alpha significance level, we have the 1 minus alpha confidence interval for beta 2 taken in isolation being given by that interval on the beta 2 plane. We then get the horizontal lines as the appropriate confidence interval on beta 1. And we get the square in this case because we're doing the tests as if they were independent. We've assumed that x1 and x2 are orthogonal, and therefore the appropriate acceptance region of the hypothesis H0, that both beta 1 and beta 2 are 0, is everything within that square. And that's the acceptance region for either this test of H1 and then H2, or H2 and then H1. If we were to perform the direct F-test, then the acceptance region, given the orthogonality of x1 and x2, and well, that's the main point, the acceptance region is a circle. This is supposed to be a circle. And the point is that it doesn't completely enclose the square, nor does the square completely enclose the circle. So that there are particular regions of the parameter space where, for example, if we were in this region for the true model, the sequential tests would not reject H0. And yet, we're outside the acceptance region for the direct F-test. So that if we were in that region of the parameter space, the F-test would reject H0, and either of the sequential tests would not reject. Alternatively, if we're in a region like that, we would find that the F-test would not reject H0, and yet the sequential test would reject H0. Obviously, an important point here is the choice of significance levels for the t-tests and the f-tests to ensure that this acceptance region for the sequential test, which is the square, in fact corresponds to the same size overall as does the circle for the f-test. And given the simplifications in this problem, in particular the orthogonality of x1 and x2, the t-tests can be done if we're doing two-sided tests, say for t1, if that's done at epsilon 1 upon 2 level, the t-test on beta 2 is done at epsilon 2 upon 2 significance level for two-sided tests. Then the appropriate choice of the alpha significance level for the f is given by alpha is equal to 1 minus epsilon 1 into 1 minus epsilon 2. And that comes about because the tests T1 and T2 are independent in this particular structure. So that if we chose alpha, say to be 5%, and we then simplified the problem by having epsilon 1 and epsilon 2 equal, because we didn't have any preference for being more stringent on x1 or x2, then we could solve this equation. Having chosen 5% for alpha, the solution for the common epsilon would be 2.5%. So the point of this example is that when we have a composite hypothesis like H0 here, then it's quite possible that a uniformly most powerful test doesn't exist. And we see in this example there are regions of the parameter space where the f-test is preferable, and there are regions of the parameter space where the sequential t-tests are preferable. So that we can't say that there's uniformly most powerful testing procedure. However, there are special cases of composite hypotheses where uniformly most powerful testing procedures do exist. And I want to consider one of those next. And that's the situation where we have uniquely ordered, nested hypotheses. And an example from Econometrics would be a simple distributed lag model with a conditional expectation of the dependent variable yt conditional on the current and lag values of an explanatory variable x is given by the sum I is 1 to k beta I x t minus I. We could in fact have that going from 0 to include the current x. And if our problem is one of deciding the order of that distributed lag, in other words, the maximal lag in that lag relationship, then we have in fact a uniquely ordered, nested set of hypotheses. And we could write those hypotheses as, first of all, H1 beta k bar, where now k bar is the maintained maximal value of k. So at some stage we have to specify what the maintained hypothesis is. That implies that we fix some maximal value for k. We denote that by k bar. And the first hypothesis is that we don't need to include the k bar lag on x. The second hypothesis, which is now composite, is that both beta k bar and beta k bar minus 1 are 0. And this is equivalent to saying that the order of the distributed lag is now at most k bar minus 2. And we can go on in that sequence until we come to H12 through to k bar, which would be that beta k bar is equal to beta k bar minus 1 which in turn is equal to beta 1, which is equal to 0. And so the distributed lag is of order 0, and there's no lag at all. Notice that we only get this uniquely ordered nest of hypotheses if, in this particular example, the problem we're interested in is determining k. Once we've determined k, we might then be interested in finding out whether the lags lower than order of k that we've just determined are in fact included in the model. But that's an addition to the problem we're looking at. The problem we're looking at is simply determining the maximal lag in this relationship. And the uniquely ordered property comes about because if in fact H1 was false, at that stage we know we don't need to go on and test any of the succeeding hypotheses because they must also be false. Because every one of the succeeding hypotheses embodies H1. So if at this stage we found H1 to be false, all succeeding hypotheses must also be false. That discussion was in terms of true and false, and in practice that's non-operational because we don't know what the true model is. We could alternatively say that if we reject H1, then we know we would reject all succeeding hypotheses, provided we'd chosen the appropriate significance levels for the test. And therefore, at that stage, we don't need to go on and test any further hypotheses once we've found H1 is rejected. Equivalently, if H1, 2 through to k bar is found to be true, then all preceding hypotheses must be true. And making that an operational description, if this final most restricted hypothesis has not been rejected, it follows that all previous hypotheses wouldn't be rejected if they were tested separately. And that's the essential characteristic of a uniquely ordered, nested set of hypotheses. Well, in this situation, we can consider a particular sequential testing procedure, and it turns out to be an optimal sequential testing procedure in the sense that it's uniformly most powerful. And a reference here is T.W. Anderson, who discusses it in a number of places in his book on time series analysis. So that's his book of 1971. Though in fact he discussed the problem in the Annals of Mathematical Statistics in 1962. Other people have also discussed this procedure, but Anderson seems to be the person who's discussed it more frequently than anybody else. The procedure consists of starting from the most general hypothesis. And the most general one is, of course, the maintained, which I denote by HM, and that's the model we have at the top of the board when we make k equal to k bar, the maintained maximal value. We then test the first restriction in the sequence. So we test H1 against the maintained hypothesis. And that's equivalent to testing the hypothesis that beta k bar is 0. If we reject that hypothesis, we stop in the sequence, and we would certainly have rejected the most restricted hypothesis. If we do in fact reject this first restriction, the model we accept is the immediately preceding one, which is the maintained. And if ever you're going through an ordered sequence of hypotheses using this sequential procedure, and you find that you reject the first restriction, then the first thing that ought to run through your mind is that you probably haven't chosen the maintained hypothesis to be general enough. So at that stage, you would consider revising HM, the maintained. However, if we perform this test and we don't reject H1 relative to the maintained, the next stage is to test H12 against H1. And that is equivalent to testing whether beta k bar minus 1 is equal to 0. The next test, if this is not significant, is H123 against H12. And that is equivalent to testing whether beta k bar minus 2 is 0 or not. And you go on through this sequence of tests until you come against a significant result. So you get a significant test statistic. At that point, the model which is accepted is the immediately preceding one. And that is the optimal sequential testing procedure, when the problem is to determine, in this case, the order of the distributed lag. But this problem could be one of determining the order of an autoregression. It could be one of determining the order of a polynomial trend, or any other similar uniquely ordered nest of hypotheses. Well, a number of comments on the procedure. Notice that in this particular context, if, when we wrote out the model with the error term included, we'd assume that that error term was normally distributed and that the x's were fixed numbers, then each of these tests could have been performed by a t-test. So each of those would have been t statistics. If in fact the model is more general and we can only get asymptotically valid test statistics, then the appropriate test statistics derived either using the Wald testing principle, the likelihood ratio, or the Lagrange multiplier would all be asymptotically chi-squared with 1 degree of freedom. Because we're going through the full set of restrictions, taking an additional restriction into account each time, considering them one by one. So every one of the test statistics has got 1 degree of freedom. Though the testing could be done on either the Wald, likelihood ratio, or Lagrange multiplier principles, in fact, for most problems, it's likely that it would be either the Wald or likelihood ratio principles that are involved. For most problems, it's more complicated to calculate the Lagrange multiplier test statistics. And in fact, given the presence of a particular program that Professor Sagan has written to compute Wald test statistics in general, it's quite likely for any set of hypotheses of this type, you would in fact use the Wald testing principle, because it only involves the estimation of the parameters on the maintained hypothesis, and then, as a function of those unrestricted parameter estimates, you can in fact test every one of these hypotheses. Whereas if we were to use the likelihood ratio, we would have to estimate the model corresponding to every one of these hypotheses. So the first point is that there's 1 degree of freedom for every test. The second point I've already made, but it's worth listing again, that we accept the model corresponding to the hypothesis immediately preceding the significant test. The problem that we're faced by when we have a uniquely ordered nest of hypotheses is one of balancing the costs of over-parameterization against the costs of under-parameterization. In this particular context, the costs of over-parameterization are that we decide on a value for k which is larger than the value we really need, or alternatively, which is larger than the true value of k. That means, if we make that error, that we've included too many x variables, and as a result, the estimates of the betas will be inefficient. So the first cost is one of inefficiency. The second cost is that of under-parameterization, and that is that we choose a value of k which is less than the true value, so that we haven't included enough variables in the model, enough lags in the model, and as a result, the estimates of the betas will be inconsistent. The only case in which the estimated betas would be consistent is if all the variables in the regression were orthogonal. But in this particular example, where it's a distributed lag, and we're assuming that the x variable is some economic time series variable, then those x's in the regression are most unlikely to be orthogonal. So that in general, when we under-parameterize for this problem, the resulting parameter estimates will be inconsistent. So the problem we're faced with is balancing the costs of inefficiency against the costs of inconsistency in estimation. And the Anderson procedure essentially proceeds by using classical statistical methods of, first of all, fixing the type 1 error probabilities. And a type 1 error in this context is accepting a model which is more general than the true model. So in the Anderson procedure, we're fixing the probabilities of getting estimates which are inefficient. And subject to that, we want to minimize the probability of type 2 errors. Type 2 errors, in this context, involve selecting a value of k which is smaller than the true value of k. In other words, type 2 errors involve inconsistency in estimation. And what Anderson was able to show is that among the set of procedures which fix probabilities of type 1 errors, in other words, fix probabilities of inefficiency in estimation, this particular procedure is uniformly most powerful. That particular result was derived in the context of non-stochastic regressors, or non-stochastic x's. In fact, he was determining the order of a polynomial in a trend. When we come to more realistic economic applications, the result can only be an asymptotic one. And so the discussion of the properties to be absolutely strictly correct are much more complicated. but in general we can say that it does have desirable power properties. As to whether a procedure which has those properties is a good one will depend very much on your particular problem. But notice that you do have a number of parameters at your disposal to control the overall properties of the procedure. And the first one at your control is the maintained hypothesis. The next set of parameters at your control are the probabilities of type 1 error for each of the tests in the sequence of tests, which I'll denote by epsilon 1, epsilon 2, through to epsilon k bar. And by appropriate choices of these, you can adjust the properties of the procedure. In particular, if you choose the maintained hypothesis to be at least as general as the model you believe is likely to be needed from your prior information about the problem involved, and you choose the significance levels for the first tests in the sequence to be very small but increasing, then a procedure like this optimal Anderson procedure does in fact seem to be a desirable procedure, because at the first stage you've chosen a very general model. In fact, it's more general than you're likely to need. You then choose very small probabilities of type 1 error for the first few tests, which then means there's a very small probability that you will in fact choose one of those very general models. But at least there is a non-zero probability that you will choose them. And so if one of the very general models is needed, it's quite likely you'll find that out. Alternatively, if in fact the model that's needed is one of the highly restricted models, because we've chosen the significance levels to be small originally, and because of the property of the procedure which I want to discuss in a minute, the probability of choosing a small model is in fact quite large. So for models of the type I presented, namely distributed lag, provided you choose the maintained to be very general, and then choose the significance levels initially to be small but increasing, an Anderson procedure does in fact appear to be a reasonable procedure. Call that point 3. Point 4 now concerns specifically the uniformly most powerful property of the procedure and an intuitive discussion as to how that comes about. And in fact, the property of the procedure comes about because of a number of characteristics that the procedure has. First of all, each test statistic in the sequence of test statistics depends only on the validity of preceding hypotheses in the sequence. And not on the validity or otherwise of succeeding hypotheses. Secondly, all the test statistics are, in the simple models that Anderson first considered, independent for all sample sizes, but more generally are asymptotically independent. And the third important characteristic is that each test in the sequence is in fact a test of a simple null against a simple alternative. Simple null against a simple alternative. And so if we work backwards through these properties, because each test statistic is of a simple null against a simple alternative, we know that a uniformly most powerful test statistic will exist. Secondly, because all the test statistics are independent, when we now test a joint hypothesis through this sequence of tests, they will all, the test of the joint hypothesis will, as a consequence of the independence and each test itself being uniformly most powerful, produce a uniformly most powerful test of the joint hypothesis. And these two are the important properties of this sequential procedure, which result in it having overall a powerful property. The first statement is involved in the proof of the independence in the second statement, and that's why it's an important property. Following on from the independence of each of the test statistics, we have that if we now consider testing the joint hypothesis H12 through to S against the joint H1, 2, 3 through to R, when R is greater than S, in other words, H1, 2, 3 through to R embodies more restrictions than H1, 2 through to S. When we consider testing this hypothesis against the first, because each of these test statistics are independent, what you're able to show is that the direct chi-squared test statistic, which would have degrees of freedom R minus S, of H1, 2, 3 through to R against H1, 2, 3 through to S, that would be the direct test of those, is in fact equivalent to a test which is the increment in the chi-squareds. And furthermore, this test statistic, which is the increments in the values of the chi-squared, is independent of chi-squared for S restrictions. In other words, the test statistic for this first hypothesis. And this is essentially why it's possible to test a sequence of hypotheses using the wall testing principle very simply. You estimate the parameters of the maintained hypothesis. You can then compute directly each one of these direct test statistics where the unrestricted model is in fact the maintained hypothesis, so that those are all factor of degree R when you compute all those for R running from 1 through to the maximal number of restrictions. You can then go through and perform the Anderson optimal sequential testing procedure by looking at the increments in those chi-squared test statistics. And that's a very convenient way of doing the sequential testing. So that the testing procedure would be compute the statistic which has got a chi-squared with 1 degree of freedom for the first restriction in the sequence. The next statistic would be compute the difference between the statistic for the direct test of the first 2 restrictions and the direct test of the first restriction. The next one would be the chi-squared for 3 minus chi-squared for 2, and so on through the sequence. The final point on this optimal procedure is choice of significance levels. And when we do choose the epsilon 1, epsilon 2 through to epsilon k bar, what does that imply for the overall significance of the induced tests of H0 against the maintained, when H0 is the composite hypothesis of all the hypotheses in the sequence? In other words, the test of the most restricted model against the maintained. Well, the answer is, again, because of this independence, that the significance level alpha for the test of H0 against HM is in fact given by 1 minus the product I is 1 k bar of 1 minus epsilon I. And the importance of this is that the significance levels for the induced test of a particular hypothesis against the maintained, when we vary k bar, form a non-decreasing sequence. So that the more restricted the model is that we're considering a direct test of against the maintained, the higher the significance level if we use the same epsilons. This result also helps us to control the overall significance level for the test. Essentially what we're interested in is alpha. If we really are interested in H0, but we're saying in addition we would like to know if H0 is rejected, which intermediate hypotheses are causing that rejection, and that's why we've gone into this procedure. But if we are interested in H0, then it's the significance level for the test of H0 against the maintained that we really want to control. If we want to control that, we can do it via this relationship. And so if we want to choose the epsilons when they're all different, we would have to introduce some special or particular scheme defining the epsilons as some function of I, and then substitute in here with a particular value of alpha, which may be 5%, and solve for the corresponding epsilon i's. The simplest thing to do is to assume that all the epsilons are in fact the same. So every test in the sequence will be done at the same significance level. We can then substitute in here 1 minus epsilon to the power k bar and solve that, which when we fix alpha at some particular level for epsilon. A few comments on other procedures when we have a uniquely ordered nest of hypotheses. And the first alternative procedure to consider is the obvious one of reversing the order of the testing. What we've done in the Anderson procedure is to start from the most general model and work progressively towards the most restricted. The reverse procedure would start from the most restricted model and then sequentially consider whether you need to generalize the model. And putting it in those terms, this is equivalent or analogous to a sequence of Lagrange multiplier tests. That you set off with the most restricted model, you then consider whether you should, in fact, have a slightly less restricted model, and so form a test statistic of the need to have a more general model. If as a result of that test you decide you need the more general model, you can then compute another test statistic to see whether you should have had an even more general model. And in that way, you have in effect a procedure which is analogous to having a sequence of Lagrange multiplier tests. This, in fact, is the procedure that many people do use in practice in econometrics. They often start with a very simple model and then, again, often not very systematically, but they search for the need to generalize the model they would like to end up with. So it's interesting to know what statistical properties the reverse procedure has. And unfortunately, it's very difficult to say anything at all about the statistical properties of it. First of all, because with the reverse procedure, there's no need to specify what the maintained hypothesis is before you start testing. In fact, the maintained hypothesis need only be the last model that was needed to be considered. If you don't specify the maintained, then immediately it's very difficult to consider the power of the procedure. But it's also difficult to consider the power of this particular procedure because the test statistics in the sequence are no longer independent. So the test statistics for the reverse procedure are not independent. And so it's virtually impossible to say anything at all about the power of that procedure. Another procedure would be to work from the most general hypothesis and consider sequentially increasing the number of restrictions, but perform the tests of H1 against the maintained. In other words, that first test is exactly as in the Anderson procedure. But then test H1, 2 against the maintained. So if we don't reject H1, we then consider H1, 2, but we don't test H1, 2 as in the Anderson procedure relative to H1. We test it relative to the maintained. And so on through the sequence that H1, 2, 3 is then tested against the maintained. And in fact, this is the procedure that was suggested, among other people, by Godfrey and Poskett for the problem of determining the optimal order of the Ullmann polynomial for a distributed lag. And that was in Journal of the American Statistical Association, 1975. Well, what can we say about the properties of this procedure? Well, in fact, it's possible to show that this procedure is less powerful than the Anderson procedure. And essentially the reason for that is that the first test, we're testing the first restriction. That's just as in the Anderson procedure. In this sequence of tests, the second test tests jointly the first and the second restriction against the maintained. In other words, we're now testing whether the first and the second restriction are valid jointly against the maintained, ignoring the fact that we've already tested the first restriction. And the Anderson procedure, by testing the two restrictions involved in H1, 2 relative to H1, is now in fact only testing the second restriction, conditional on the first restriction being valid. So that by using this procedure, which was suggested by Godfrey and Poskett, for example, you are in fact ignoring information at each stage in the sequence. And as a result of that, you're able to show that this procedure is less powerful. That's all I want to say on uniquely ordered nested hypotheses. What can we do in the situation that the hypotheses are in fact not uniquely ordered? Well, the first possibility, and the one that I want to illustrate by the application of choosing production functions, is an exhaustive search procedure made up of a first stage where we arrange the hypotheses into all feasible orderings. Feasible is introduced to say that there will be some orderings which are possible, but on prior grounds we're going to reject as being uninteresting in our particular problem. And apply optimal sequential tests within each of those ordered nests of hypotheses. So that as a result of this first stage, we'll have as many selected models as we have ordered nests of hypotheses. The second stage is then to choose among those preferred models. So we select single preferred model from the set generated by the first step. At this second stage, a complication that can arise is that the hypotheses in the set of preferred models from each of the nests in stage 1 may not be nested within each other. So at stage 2, we may have to use procedures for discriminating between non-nested hypotheses. So non-nesting is possible among the hypotheses in the set, and so we might have to use procedures for discriminating between non-nested hypotheses. What are the drawbacks of that procedure? Well, first of all, it can involve a very large number of tests. Secondly, the tests at the second stage are not independent, which now means that it's impossible to argue that this procedure is uniformly most powerful. The best that you could argue is that it has reasonable power properties. And thirdly, as a consequence of there being a very large number of tests, the overall significance level, when we consider the most general the most restricted model, or alternatively, the model we select in the end, as being tested against the most general, is likely to be very large. As a result of the large number of tests. In other words, we may as well not have tested some of the restrictions. If you've got a very large significance level, you may as well forget about testing some of those restrictions. So that if you are going to use this exhaustive search procedure, you must be very, very selective in choosing the ordered nests for stage 1. And really only choose a small number of nests which you believe do have some relevance to your problem. By doing that, you will then reduce the number of tests which count as point A and directly will help in point C. Well, another possibility, and the one that I would most strongly recommend for non-ordered nests of hypotheses, is that although the problem as originally specified doesn't have an ordering, you impose an ordering on it using your prior information about the problem. And an example of that is a two-stage testing procedure for dynamic specification, which I want to consider later. Thirdly, impose structure on the problem as opposed to imposing ordering on the hypotheses by introducing an explicit loss function. And so 3 is saying, accept the fact that you have a multiple decision problem. Therefore, define your loss function and find a procedure which is going to minimize the risk for your specified loss function. At this stage, I was going to discuss simultaneous confidence intervals as another alternative approach to the problem of non-ordered hypotheses and Bonferroni inequalities. I would prefer now to continue by discussing the application of the exhaustive search procedure, which is what I've got prepared on the board, and delay the discussion of simultaneous confidence intervals. So the example I want to discuss is the example in my paper, which is appearing in Econometric in July 1977. And essentially the problem is one of choosing from a set of functional forms for a production function the best functional form for a particular set of data. And the reason why I was interested in this particular set of functions for the production function is that by looking at these, we can test a large number of hypotheses about the elasticity of substitution between factors of production. And in these examples, we have 3 factors of production: N, the employment of people; K, the employment of capital services; H, the number of hours worked. And to treat the number of hours worked as a separate variable was first considered by Feldstein in the 1960s, and has since then proved to be a useful specification for production functions. So within the class of models which have constant elasticities of substitution between these 3 factors of production, I wanted to select for a particular data set the preferred model. In addition, I wanted to discriminate between these models with an additive error and a multiplicative error, so that we could have, for example, the 5th function plus a random error term, or in the case of function 7, we could introduce a multiplicative error term where we have exponential of u. So that the first problem of interest is hypotheses about the elasticity of substitution between factors of production when I and j are employment, hours of work, and capital. Secondly, we're interested in whether the appropriate error structure is additive or multiplicative. And thirdly, we're interested in the degree of returns to scale. And in particular, whether there are constant returns to scale, which for most models is the hypothesis that nu is equal to unity. So these were the hypotheses of interest. Within this first set, the hypotheses on the elasticity of substitution, we have the whole range of elasticity of substitution embodied in these 9 functional forms for production functions. Well, when we look at these 9 functional forms, using the diagram on the far right, and look at the structure relating these functions, we can see that we have in effect 3 maintained hypotheses, 3 most general models, F1, which is the Mukherjee production function, F2, which is the Sato 2-level constant elasticity of substitution production function, and then a trivial example, F6, which is just a simple CES production function. Within each of those, the remaining 6 functions are nested, but they're not uniquely ordered within that nest. And in fact, we can move directly from F6 to F8, which is a Cobb-Douglas function, and that particular section of the tree does give us, in fact, a simple null hypothesis against a simple alternative. So there is, in fact, no problem in testing F8 against F6. That's a simple testing problem. But whenever we consider either F9 or F8, both of which are Cobb-Douglas production functions, as being special cases of either Mukherjee or Sato, then there are a large number of routes we can follow through this tree to get from those maintained to these most restricted models, which means that we don't have a uniquely ordered nest of hypotheses. What can we do in that situation? Well, what I did in this particular example was to use the exhaustive search procedure, and that is to construct each of the feasible ordered nests, which we have on this part of the board. If we consider the maintained hypothesis of the simple CES function, then we label that as nest 1. The functions there are the maintained F6 and the restricted within it F8, the Cobb-Douglas. So we have a simple test of F8 against F6. When we come to the Sato function, we have in fact got 5 possible nests. In other words, 5 routes of moving from F2 through to one of the 2 versions of the Cobb-Douglas production function, either F9 or F8. For the Mukherjee, we have just 2 nests, or 2 routes in moving from F1 through to either F8 or F9. The exhaustive search procedure consists of applying the Anderson sequential testing procedure within each of these nests, which will then give us a preferred model for each of those nests. So that if I ring models which were selected, these aren't in fact the exact results in the paper. This is just an illustration. we may have got the preferred models within each of these ordered nests to be F8, 7, 8, 7, 9, and so on. The next stage in the exhaustive search is now to discriminate between each of the ringed models. And since the ones that I've ringed are in fact all Cobb-Douglas production functions, F7, 8 and 9 are all of the Cobb-Douglas type, we would originally think that they're all nested within each other. But in fact, we don't have that situation. We don't have correction. We do in fact have each one of those nested within the most general, which is F7. So that F8 is nested within F7 by imposing the restriction that alpha star and beta star are equal. F9 is nested within F7 by imposing the restriction that gamma star is 0. So that with these examples of preferred models from the nests, the second stage of discriminating between those can be done still using classical statistical procedures, because we have a nested set of hypotheses. But notice that all I've discussed so far is choice of the functional form. In other words, hypotheses concerning the elasticity of substitution between the factors. Those hypotheses are not independent of the hypotheses about the error structure. In other words, the decisions that we take on functional form are not necessarily independent of the choice we've made for the error structure. Also, the decisions we make at this first stage are not necessarily independent of hypotheses we have about the degree of returns to scale. The hypotheses in 1, 2 and 3 are not uniquely ordered, nor are they orthogonal to each other. So again, we have a situation where we've got non-ordered hypotheses. And what I did in the application was now to impose an ordering and to say that I will first of all consider the functional form. Having determined the functional form, I will then determine what the appropriate error specification is. Having determined both functional form and error specification, I'll then test whether there are constant returns to scale. And that procedure is going to be a reasonable procedure if you believe that that ordering of the hypotheses is reasonable, which I did. So that final stage in the testing gives an example of selection when you don't have uniquely ordered hypotheses by imposing some ordering on the hypotheses. The testing for error specification, whether it's additive or multiplicative, was done by only estimating a model with additive errors and then separately estimating the model with multiplicative errors. Those two models are nested within a more general model, and that more general model is the transformation model of Box and Cox, which I referred to in the last lecture. Because in effect, the models for the production function are yt, some nonlinear function of theta, xt, and then either plus ut or log yt is the log of g of theta and x plus vt. And this is the multiplicative error specification. And we can nest those two models in the model which considers y star as a function of g star theta xt plus u when y star is yg to the power lambda minus 1 upon lambda, and similarly for g star. In other words, that is the Box and Cox transformation. When lambda equals 1, you get the additive error specification. When lambda equals 0, we get the multiplicative error specification. So that these two hypotheses are nested, and the testing was done using the likelihood ratio criterion. In other words, just comparing the values of the maximized likelihood functions. In computing the test statistics within each of these nests, since these models are nonlinear regression models, the test statistics only have asymptotic validity, and so on either the Wald or likelihood ratio testing principles, we had asymptotically valid chi-squared test statistics. What I did in the paper was to modify those test statistics to correct for the possibility that in small samples the models with large number of parameters may overfit. And that was done by using the suggestion of Box in 1949, which for the likelihood ratio test statistic was to, instead of taking minus twice the log of the likelihood ratio, take minus m 2m upon t into the log of the likelihood ratio, where m is equal to t minus k minus 1 plus r upon 2, when k is the number of parameters in the unrestricted model and r is the number of restrictions being tested. And this will get the size of the test statistic nearer to the notional size in small samples. In other words, it will correct for the possibility of highly parameterized models overfitting in small samples. Arising out of this paper, there are also a number of computational points, but since they're directly related to other considerations like the Bonferroni inequalities, I'll leave the discussion of those until the next lecture.